everyone to GJ Tech School. Grand journey into learning civil engineering basics and concepts. We are discussing concrete technology series and the topic of learning is concrete mix design. This is session 3. So we have completed the introduction and ingredient session in video 1, and we have discussed the methodology or the procedure of mix design as per the Indian Standard Code in video 2. So viewers who have not gone through those two videos, kindly check the link below and do watch those videos for better understanding. In this session 3, we are solving the step number 6 of methodology, that is illustrative part. So I have taken up a problem from an examination question paper and have tried to illustrate the aspects and how do we exactly mix design a concrete for the respective grades. So let's begin. So brushing up the basics from the previous class or previous video or previous discussion, here are the references of different design variables, so we can go through this once before we begin solving the problem. So target mean strength, the references, approximate air content, the references, water content in cubic meter, references. So next variables are water cement ratio, references, and cement content, references, volume of coarse aggregate, the references. So they are referred from individual tables and figures for the respective parameters of references from IS 10262, also for certain parameters or variables from IS 456 2000. So data stipulations given for mixed design of concrete are as such: design a concrete mix for M25 grade concrete, and grade designation is M25. Nominal size of aggregates 20 mm, down size, that is maximum is 20 mm, minimum cement content is 300 kg. It is given, or that also can be obtained for the exposure class. So what is the exposure class? It is moderate, and the use of concrete is RCC. Why it is quoted is sometimes we do have to know the values of plain concrete or RCC concretes on site than for solving the examination problem, because the concrete, when it is goes for mass concrete, the air content needs to be checked on trial and experience basis, and also while referring for the force aggregate proportions and other parameters, we need this usage of concrete, whether it is an RC concrete or plain concrete. So maximum cement content is 450 kg per meter cube. Fine aggregate should conform to zone 2, it is prescribed. So SIEM analysis conducted on fine aggregate before they are confirmed for using in the mixed design should be verified with the table 9 in IS 383 and should conform for the actual retaining portions on each sieve sizes as prescribed in the table 9. Other test data are specific gravities of all the ingredients like cement and coarse aggregate, fine aggregate, water absorption and surface moisture tests, and their values respectively for coarse and fine aggregates needs to be quoted. So it is given. We can observe there is no free surface moisture for coarse aggregate, but a free surface moisture is available for fine aggregate. This indicates that fine aggregates is wet. So all these points to be noted, or while solving or before going to the mixed design thoroughly, we need to understand the data given in order to design the concrete with a better precision. So after knowing the design data or stipulative data required, better remembering any data missing out, we have arrived at a table in the second video or in session 2, that I have given a table where we can remember better of in a consolidated manner of all the data, including material data, test data and other details. So let us go through quickly through this table and confirm all the data are available. So cement type is given and minimum and maximum content cement content is given. Cementitious materials need not be used. Coarse aggregate maximum nominal size of are given as 20 mm and type of coarse aggregate is missing. So here we can note that this data should be assumed as whether rounded aggregate or angular aggregate. So fine aggregates type or conforming grade is zone 2. It is given. Chemical admixture not to be used. It is prescribed. So moisture content, test data of coarse and fine aggregates are moisture content and water absorption. Sieve analysis is a common test that is conducted for in order to grade or in order to qualify the aggregates for use in concrete as given in IS 383 table 7 and 9, and they should conform for the maximum size retained and different size sieve sizes. So specific gravity is one more test data required for all the materials, that is also given in our question. Other data or details like workability is given as 75 mm. Method of placing concrete is prescribed as manual method, and degree of control, if it is not given also, we consider the very good quality. Good quality is to be considered as the degree of site control. So before starting up the design or before solving any example, I follow one policy that is coming from back to front, that is coming up in keeping in mind the results where we have to uh, go after solving any problem. That is, in the current problem of mixed design, the final outcome will be the mixed proportions, that is cement content, coarse aggregate content, fine aggregate content, water content, chemical admixture content, and free water cement ratio. So we need to arrive at all these aggregate all these concrete ingredients. One more thing has to be again remembered is we need to have a clear picture of what are the different variables. So I'm reminding the different design variables once again here, or the different steps or computations required in mixed designing of concrete. So there are 8 design variables. We need to calculate target mean strength stepwise. The second step is air content, third is water cement ratio, fourth is water content, fifth is cementitious content, tabulation or computation, sixth is admixture, seventh is aggregate contents, and eighth is coarse aggregate proportions. So everybody should remember these steps and always try to follow these order so that it makes the design process simple. So solving the problem, first step or first variable is target strength. So target strength is calculated from the two formulas. One formula uses the standard deviation and the second one uses the factor depends upon compressive strength of concrete, that is X factor. And the values for these two are obtained from table 1 and table 2. So X value is obtained for the grade of concrete. So here we are designing the M25 grade of concrete. So you can see the table 2 shows the standard deviation values, that is value 4. So standard deviation value is 4, and for X value we are referring the table 1, and the respective value of X for M25 grade is 5.5. Then there is a correction for target strength only in case of rounded aggregates are used in mass concrete. So this correction also made for when there is a wet sieving made before the cube casting is made for compressive strength test, and here there is no rounded aggregates used, hence we can discard any changes, and directly the target strength value is 31.6, that is higher of the values from both the equations. The second is air content or entrained air, and these factors which are required to compute air content are maximum size of aggregate, in our case it is 20 mm, and grade of concrete it is M25. So it is a standard grade or it is not a high strength grade concrete, so we need to refer table 3 of IS 10262. So what does table 3 say? For 20 mm maximum size of aggregates, the entrapped air content to be considered for design mix of concrete is 1%. Next is water cement ratio. Here in this particular problem, water cement ratio is given for the exposure condition moderate and for RCC type concrete. So in general, water cement ratio on site or while solving a problem, we need to calculate or compute from the figure 1. So how does it look like? This is the figure 1 in 10262. Three curves are given. Curve 1 refers to OPC cement grade 33, curve 2 refers to OPC cement grade 43, and curve 3 refers to OPC cement grade 53. So in our case it is OPC cement grade 43. If the water cement ratio was not prescribed, we would have referred this curve number 2 and the 28 days compressive strength of concrete in y-axis would have been our target strength. So for these two respective values we would have obtained the respective water cement ratio. So for now, for this particular problem, let us consider it to be zero point 0.5 as given in the question. So checking for maximum water cement ratio, we have to take the maximum allowable water cement ratio for the exposure condition moderate in table 5 IS 456, and that doesn't exceed, hence it says okay. So next variable is water content. Water content is referred in tables against maximum size of aggregates. So we need to refer table 4 as the grade of concrete is less than M65. So table 4 gives the values for 20 mm MSA as 186 kg. So there are corrections to be applied for water content, that is corrections for angularity of aggregates if rounded aggregates are present. So there are no rounded aggregates, no corrections, and no chemical admixtures used. So there won't be any reduction of water content, or there won't be any correction for chemical admixture. And the third type of correction is only correction for slump. So the table values are given for the value of a slump of 50 mm, but the current problem the slump is 75 mm, so there is an increase of 25 mm slump. For correction needs to be applied at 3% for every increase of 25 mm slump can be adopted, and we can increase this 186 kg of water content by 3%, and we obtain a value of 191.58 kg that can be rounded to 192 kg per meter cube of concrete. Next is cement content. Cement content is calculated from water cement ratio. So water cement ratio is 0.5. So water content is 192 kg per meter cube. So simplifying and solving, we get a value of 384 kg per meter cube. So cement content, you need to keep in mind, needs to be checked for minimum cement content. So minimum cement content provided, or it's need to be referred from table 5 IS 456. Here in the current problem it is provided, hence it is provided as 300 is kg per meter cube as minimum cement content. So the obtained cement content from the calculation is 384, hence okay. And there is a correction for cement content when we are using the SEMs or mineral admixtures. In the current problem we are not using any SEMs or mineral admixtures, hence there won't be any alteration or adjustments to the cement content. The sixth variable is coarse aggregate proportion for unit volume of total aggregate content. So this is tabulated, or this coarse aggregate proportion depends upon the fine aggregate zone, maximum size of aggregate, and water cement ratio. By default the table 5 or the values obtained is for a water cement ratio of 0.5, and for standard grades of concretes we need to refer table 5 in 10262. So table 5 looks like this. So it reads volume of coarse aggregate per unit volume of total aggregates for different zones of fine aggregate for water cement ratio of 0.5. So nominal maximum size of aggregates are 20 mm. So volume of coarse aggregate per unit volume of total aggregates for zone 2 is 0.62. So this is how we read the coarse aggregate value from the tables. So coming back, so we have obtained a coarse aggregate proportion of 0.62. This is not the total volume of coarse aggregate, this is the proportion of coarse aggregate in the total aggregate content. So we have not yet calculated the total aggregate content, but before that also we can know that portion of coarse aggregate in the total aggregate is 0.62, means 1 minus of 0.62, the remaining will be the fine aggregate proportion. So any adjustments needs to be considered? No adjustments, because water cement ratio is 0.5, so there won't be any adjustments, and there is no rounded aggregates used or chemical admixtures used, so there won't be any variations of coarse aggregate proportion. So we continue with 0.62. So after obtaining the proportion of coarse aggregate and fine aggregate in the total aggregate of content or total aggregate volume, so what is total aggregate volume? It is the volume of aggregate when it is deducted from the unit volume of concrete that is designed, all the other volume of ingredients, we get total volume of aggregates. I'll repeat. Total volume of aggregate is the aggregate volume in the concrete that can be obtained by deducting the volumes of other ingredients such as cement, water, air, and admixtures from the volume of concrete designed, that is unit volume of concrete is 1. So here we have computed volumes of water, air, and cement. There is no chemical admixtures, so we need not worry about that. So volume per meter cube is equal to weights per meter cube divided by specific gravity into 1 over 1000. So how do we compute volume of each ingredient, since we have weights of each ingredient? So we need to compute the volume of cement, volume of water, and volume of air by using this equation, which says weights divided by specific gravity multiplied to 1 over 1000 will yield the volumes of the respective ingredients. So cement volume obtained is 0.122 m cube. Air content at 1% of the volume of concrete is 0.01 m cube. Water volume, by taking specific gravity of water as 1, we get the value as 0.192 m cube. Admixture content is nil, so total volume of aggregate can be now computed as 0.676. In vice versa, the mortar content is 0.324. So in some particular cases, the code also specifies the minimum water content required, so we can also check. Usually it will be higher, but for special concretes sometimes this also to be checked up with the minimum water content required. So here we are not doing that. So coarse aggregate volume, now we are computing the actual volume of coarse aggregates to or in the volume of concrete of unit volume and fine aggregate volume. How do we do that? Total aggregate volume multiplied by the coarse aggregate proportion obtained from the table, we get the value of 0.42 m cube. So in a total volume of 1 m cube of concrete, 0.42 m cube is coarse aggregate and 0.26 m cube is fine aggregate. So together making up to aggregate volume of 0.676. So that equates the equations. So mass of aggregates. So aggregates also needs to be converted from volume to weight. So we don't have the weight of aggregates, we have the volume of aggregates obtained. Hence, how can we convert the volume to weight? Again, by using the specific gravities. So here the mass of coarse aggregate in kg per meter cube can be computed by the volume multiplied by specific gravity multiplied by 1000. It gives up 1176 kg of coarse aggregates, and fine aggregates similarly is 689 kg per unit weight of concrete. So after obtaining the quantities of each ingredients in terms of kg and also in terms of volumes, we can prescribe them in the result section in terms of volumes of each ingredients and weights of each ingredients required. And there is one corrections, as we know, that needs to be made for the moisture conditions of the aggregates. Here in this current problem, they doesn't give any moisture of coarse aggregates. Hence, we can consider coarse aggregates to be in the standard saturated surface dry condition, but in practical aspects, there will be a variation of moisture in coarse aggregate also, that will be tested regularly before batching a new batch of concrete or mixing a new batch of concrete batch. Hence, now fine aggregates are given as wet since their moisture is defined in the problem or given in the data as 2% free surface moisture and water absorption of 2%. So we need to calculate the wet weight or wet mass of fine aggregates, that is given by mass of fine aggregate in SSD condition multiplied by 1 plus free surface moisture by 100. So we arrive at a wet mass of aggregate of 703 kg. So what is the additional water added by the fine aggregates to the concrete is obtained by subtracting the saturated surface dry mass 689 kg from 703 wet weight of fine aggregate. We obtain as 14 kg of water can be reduced, which will be contributed by a fine aggregate. So final water content during mixing of all the ingredients into the batch mixer or plant mixer, we need to reduce the water content and to be tabulated as 178 kg of actual water will be added. So that is the final water content in the design mix.
Thank you very much for watching. Whoever is watching this till the end, please do not forget to like, share, and subscribe. And if you really like the way I have presented, do not forget to pass it on to all your contacts and students of civil engineering. So kindly also watch the previous videos where I have covered the previous topics related to concrete mix design, and the further there will be modifications in videos I would be sharing. So do keep in touch by subscribing for additional topics of civil engineering and interesting topics of technology. Thank you very much.